Okay, let us discuss the second problem. That is an isolated rectangular footing. We have done a square footing, now it's a rectangular footing. The conditions for rectangular footing. One is the column is not square. Here the column size is 400 by 600 mm. So that is a condition. Another condition generally is due to, even if the column is square, another condition is due to the restriction in the plot dimension, because in a building we may have a corner column, but another property will be abutting to this. So if the footing size is more, then it may go to the others property. So in that case we have some restrictions. For example, here whatever it is, 12.22 is the area requirement. So if it is a square column, square footing, the size would work out to be root of 12.22, that is 3.5 meter about. So if this 3.5 meter is not available, then you cannot go for a square footing. Suppose the plot requirement based on the plot size, etc., we have only 2.5 meter available for keeping one of the width, then we need to go for 2.5 by say some 5 meter or something like that. So that is the issue. Here, anyway, that is not the case. We have no, suppose in a square footing problem or a square column problem, if that is the previous one we have done, in that we have used a 3 meter by 3 meter size. Suppose in that question, they say that there is a space restriction of 2.5 meter for one of the sides, then you cannot use 3 by 3. You need to use 2.5 by say some 4.5 or 5 meter, like that. So that is a possibility. But here in this problem, our column is rectangular one, 400 mm by 600 mm. So that is the reason for adopting an isolated rectangular footing. And one more thing, whenever the column is a rectangular one, there is no need that you need to go for a rectangular footing design. You can even use a square footing design. There is no issue in that. So these are the various conditions I have discussed with you. Wherever we have square footing or restrictions, then rectangular footing. In real field conditions, this may happen. I hope you understand what I am talking. Now coming on to this problem, our base area is, see what is the column loading, 2000 kilonewton, then 10% for self weight of a footing and backfill, that divided by bearing capacity. Here see the bearing capacity is very low. Okay, it is only 180 kilonewton per square meter. That's a very low case. So obviously, since the bearing capacity is very low, only 180, you can expect a large footing dimension. Anyway, in Kerala red soil scenario, as I have told you, it is around 250. Okay, around 250. Anyway, but this is an illustration problem, so never mind. So divided by 180, it is 12.22 square meter. Now the proportioning, that is the proportioning, you can do it as a square footing itself, that is 3.5 by 3.5 meter. Or if you have a space restriction, one side only 2.5, then you can design it as a 2.5 by 4.9 meter. Here, when you don't have any restriction and all, it is always better to uh, proportion the dimension, like you see this b here. Okay, this b, this b, this means the in plan the projection from column face, that is this projection, as well as this projection, if you keep they as same, then you have some advantages. and it is also going to be a very economic sort of design. So to proportion that, let us assume that this width is same. Let it be b. We don't know that, so let it be b and b. So when you keep it b and b, you know that the area will be 2b plus 400 multiplied by 2b plus 600, because 400 and 600 are the column dimension. So from that, b one side, b other side. So 2b plus 400 and 2b plus 600. If you multiply that, it should be 12.22, whatever we have calculated here. It should be 12.22. So that's a quadratic equation. You can solve it easily. Result is around 1500 mm, and it is always better. That is from There are many reasons for keeping a higher value than 1500. Okay, I have just added 200 mm extra. Okay, you can even add 150 mm extra. There are very various reasons. So I have added 200 mm. So I used that projection as 1700 mm. Okay. So based on this, the size now will be 400 plus 1700 into 2 by 600 plus yeah, no, 600 plus 1700 into 2. So that works out to be 3.8 by 4 meter as the footing size, and the area is, instead of 12.22, you get 15.2 square meter. So that is the initial proportioning, a easy way of proportioning rectangular footing. But this may not work always. As I told you, if you have a property issue, if you have a depth, width restriction instead of 3.8, suppose the width is restricted to 3.5, then this method cannot be adopted. What you have to do is 12.22 is given, is known, divided by 3.5 is the restricted value. So 12.22 by 3.5, it's work out to be 3.5. So you can use a 3.5 by 3.5 square footing. Instead of that, if you have a restriction of 3 meter, so 12.22 by 3, so that is in that case 3 by 4.5 meter, 1 meter that you have to use. So these are various situations, but here we have no restriction, so we adopt even or equal projections. So our size is 3.8 by 4 meter. Now let me add this. So once you got the dimension 4 by 3.8, it's a very big size. Okay, 4 meter by 3.8 is a very big size. You should know that in buildings, the column to column spacing is around 3 to 4 meter or 5 meter. So if the spacing is 3 meter, you have one column here. If another column is spaced at 3 meter, then you are in big trouble, isn't it? You cannot have a isolated footing also in that case. So such situation also may come. Here the big size is due to low bearing capacity. SBC is very low. So in such cases, you cannot go for an isolated rectangular footing. In that case, you need to go for a raft footing. Anyway, that design we don't study anyway. So we assume that, okay, space and columns are separated at higher dimensions. So this rectangular isolated footing is design is practically feasible. Let us assume and proceed. Okay, told you some of the field problems. This is what you are going to face when you go to the field, and at that time you will understand that, okay, this SR or whatever we study in BTech is different from field. Yes, correct. Whatever we study from BTech classroom is quite different from the actual field condition. One of the example I told you, that is 4 meter by 3.8 meter, and if the column is spaced at 3.5 meter, you cannot provide this. It's an example of difference between classroom and practical real field. Anyway, having stated that, let us proceed further. So QU, that is a net soil bearing pressure we need on ultimate loads to calculate the shear design, to do the shear design. So for that we need to factor it by load factor 1.5, that is the ultimate load, 20,000 into 1.5 divided by the selected footing dimension. So you get 197.4 kilonewton per square meter as the so net soil pressure exerted by soil onto the footing, which is an inverted a flat slab. Okay, so that UDL, uniformly distributed loading, is acting on the footing slab or footing pad from below. So this is for convenience of calculation. I have converted it into Newton per square mm. 0.1974 Newton per square mm is the uniform pressure, because this is uniform. Loading is, I mean, there is no bending, so loading is uniform. 0.1974 Newton per square mm. Now we let us start designing this for one-way shear. We have calculated the pressure as 0.1974 from the footing. Okay. Now in one-way shear there are two sections actually. You know that the section is as per IS clause. We have already discussed in the previous problem. So referring the clause, you will get the info that from column phase the critical section for one way shear is at distance d. D is the thickness of one way, I mean thickness of footing. You don't know that, it's a variable. So since it is a rectangular footing, as I have shown that there, this is one of the section, and this is another section. Okay, and the projection is 1700 we have selected. So this is 1700. So 1700 minus d is the uh, width of the, I mean, area to be considered. So this one. Similarly, since it is a rectangular one, the other width is, even though the width is same, length is different. So two particular sections we need to consider when we design one-way shear. But if I will show that when this 1700, that is a projection beyond the column, is same, your calculation is quite easy. So these are the two sections. So the section number one, that is this one, I have calculated VU1. VU1 is 1700 into minus D into, not 3.8, this is 3800. Okay, 3800 into 1974 is the soil pressure which we have calculated. That is for section number one. Section number two, this is 4000, not 400. 4. So that same width 1700 minus d, width is the same into 4000 into 0.1974 is the soil pressure, net soil pressure. So that is VU1. Now if you check the VC1, that is VC1 is the resistance of concrete at this particular section. That's a phase actually. So that is of course this is not 3 point, this is 3800. 3800 into d, depth we don't know. So that face area multiplied by tau c, that is for section 1. For section 2, that is another section, it is 4000 into depth d into point tau c. So tau c we are as in the previous problem, we are selecting it as 0.36, assuming pt as 0.25, and here the table 19 will tell you tau c as 0.96, sorry, 0.36. Okay, now the VU1, VC1, you are supposed to equate it as in section 1 or section 2. So you can see that same terms are going to get cancelled. For example, here you are supposed to equate Anyway, forget about 3.8. It should be 3800. Anyway, that is going to get cancelled. That is my writing mistake. So you are going to equate these two equations. When you try to equate these two equations, similar term 3.8, that is going to get cancelled. Similarly, when you are going to equate these two, that is for section 1 and section 2, 4 term, 4.0 term is going to get cancelled. Ultimately, what you're going to get is the same equation for both the cases. So this is the same equation. This is the same equation, that is what you are going to get for both the cases. This is possible if and only if the projection from column face is same, selected as same. By some reasons, if you have space issues, etc., then this is not going to happen. Okay, so in that case, you cannot use this. So whenever you do a BTech problem or in question paper, etc., if you don't have space restriction, try to use same width or same projection beyond the column face. Otherwise, this equation 1 and equation 2, that equating whatever you are doing, that case 1, case 2 equations, that is this one and these two. When you are trying to equate, you are not going to get the same equation or single expression, you are not going to get. Then separately equate and find out D. And for the second case, also find out D. Select the higher value. Okay, I think this is only a numerical issue. You can easily understand what I am discussing. Okay, so please do it like that. But in this example, I have shown you the best way, optimized way, easy way how to solve a rectangular footing whenever you don't have any space restriction. So here, based on this, based on this, both equations are same. So you get D as to be greater than 602.5 mm. That is the case of one way shear. So in one way shear, D should be greater than 602.05. Okay. Now let us discuss about the two-way shear. Two-way shear, the section is this one. Okay, this is the section. You know that this is the section, and the distance is D by 2 by reading the relevant clause in IS 456, D by 2, D by 2. So you can evaluate the dimension. So if you evaluate the dimension and you can find out the annular area, as I have told you in the previous problem also, you can take that annular area which I have shaded, or the other area also you can take. There is no restriction. You can take this area also if you please. But when you take that, then the load in column, because it's all case of equilibration, so load in column also has to be taken equilibrated, otherwise you are going to end up in trouble. So it's always easy or preferable to take the annular area wherever you don't have any column loading. It's only the pressure from soil from below is acting. So soil pressure from below is 0.1974, you know. Now the annular area is 4 meter by 3.8, so 4000 into 3.8 minus that uh, rectangle. Size of the rectangle is 600 plus D plus 400 plus D, because the projection beyond column face is D by 2 for the critical section. So the VU2, that is two-way shear force, is this annular area multiplied by 0.1974. This area multiplied by 0.1974, and that is resisted by the face of concrete. This face, okay, this face. This size is 400 plus D. This size is 600 plus D. So that face is opposing this shearing force, that is VC2, and that area is 2 times 600 plus D plus 400 plus D into D. So that is the face area of concrete resisting that, multiplied by Ks into Tc. See, I will tell you one thing. Here you have a, when you study this, there is a very possibility of writing instead of KSTC as 0.36 as in one way shear problem. Okay, I'll show you that. This is a very common mistake. What I'm telling is, here you have in the VC1 you have used 0.36 from table 19. Okay, don't use that value in two-way shear. So don't use 0.36 in two-way shear. In two-way shear, code stipulates Ks into tau c based on the flat slab concept, and that value is Ks is maximum 1. I have explained that in the previous example, multiplied by 0.25 into root fck. Okay, so this is not 0.36. Be very careful. This is going to be 1.118, not 0.36. So this is a very common mistake that people make. I have valued many answer sheets. So from that experience, I am telling you, and this is a very sore point. This point exists in the previous problem also. There also I have told you about KS TOSI, but there is a tendency that one way shear you have taken 0.36 as the TOSI. Here, don't take 0.36. Here, TOSI concept is different. This is two-way shear. Concept is from uh, flat slab. So it is 1 into or Ks into TOSI. TOSI is not the previous 0.36. It is 0.25 into root 20 or root FCK. Okay. Now you equate and solve. So even though I have written the answer straightforward here, this is going to be very a little bit time consuming, not very time consuming, because this is also going to yield in a quadratic equation with large big numbers. So e- to make a mistake is quite easy. So how will you do the debugging? This value generally that you get will be less than previous d. What was the previous d in one way shear? 602. Okay. So this value, whatever you are going to get in the two-way shear, instead of 602, you will be getting something below that. Something below. So suppose you get here after solving the quadratic, you go to say 1500 mm. Then assume that you are at a mistake. And also suppose you get say some 200 mm. Then also understand that you are at a mistake. The value will be comparable with the previous value of one way shear. Where there we got 602. So here you are going to get something around 600. That's a method to debug. Okay, debugging, because this step it is quite error prone. Big numbers, quadratic equation, error is definitely going to happen. So please practice this slide. Please calculate the area. Oh, sorry, calculate the numbers. Get the quadratic equation by yourself. I have not presented it here. It is going to be tough, consuming, and error prone. Okay, not that tough actually, but error prone. Please do it by yourself. So two values you got for depth D. So this is from one-way shear condition. This is from two-way shear condition. Both are comparable. One is 602, other is 576. So select the higher one, 602.05 mm. Then the overall depth capital D is to be evaluated. So that effective depth plus cover 75 plus 20, assuming 20 in both the direction. That is here you need 20 mm in this direction, 20 bar in this direction in this particular footing. Okay, both 20 mm, so just minus 20. So you get overall depth 697. 697 is close to 700, only 3 mm. So it is preferable that you just add some 10 more mm. So just take it as 710 mm as D. You can proceed with 700 mm also, there is no issue. But always be on a safer side when you are in the examination. Even if you take 720, if you take 750, all those are okay. Okay, it's be very careful in selecting that. If you keep a little bit safety margin, then your numerical calculations will be fine. And that too in an examination hall. you need to consider the time available. So just make a safer value. 710 mm, I have selected it here. They don't ask me why 710. Even you can use 750 also. But don't use 1000 mm, 1500 mm, etc. It's all matter of experience. Use a higher value, safer value, that's all. But don't be that much safe. That will prove to be your design as uneconomical. So this is economical, safer depth, 710 mm. Okay. Now you got that 710 mm. So you have two directions. One is dx and dy as usual in the two-way slab also. You know the concept of dx and dy that we will use. Dx is 710 minus cover minus 20 mm dia bar by 2. Dy is, if you see, it's very, I think I need not to repeat those things. This depth is 710. You have one bar like this, another set of bar like this. So if this is dx, dx means to the center of the bar. So that is 710 minus cover is 75 mm, 75 minus 20 by 2. And this will be dy. So dy is 710 minus 75, then one main bar x bar is there, 20 minus 20 by 2. So like that you get 625 and 605, and same thing which you have done in the two-way slabs. Now we need to calculate the gross bearing pressure now, because you have assumed 10% extra in that calculation. You got the real depth, etc. So uh, you need to cross check that 10% here. So here there is a assumption as in the previous problem. Assume the depth of foundation, because this is the excavation done and we keep the foundation at a depth, and this depth is, I have assumed it as 1.5 meter. This can be varied. Suppose in the classroom or in the university exam you are doing it, and you assumed 1.5 meter, and this check is not matching, then you immediately what you have to do is reduce it to 1.0, etc., because code says zero point 0.5. So you can use any value above zero point 0.5, even though when you use zero point 0.5, in this case the foundation is going to be projected, because if you use zero point 0.5, our depth of foundation is 710, then this footing is going to be projected up by 0.21. But for examination, as a safety valve, you use any value above zero point 0.5. But generally, if you follow the steps or my advices, then you are not to end up in such a critical situation. So follow my advices. So I have selected 1.5 meter. Actually, that is one of the reason why I have kept the projection a little bit more, because we have selected even values b and b when we have solved, and we got b as 1500, but still we have selected 1700 as the projection. This is one of the reason. Because this value need to be quite less. That is the reason, one of the reason. So if you calculate that, gross pressure gross pressure is footing, sorry, the load on column divided by footing size plus, as I told in the last class, 24 is the, that is, you have this footing here, this footing here. So at a location, this is 0.71, and if this is 1.5 meter, this depth is going to be 0.79, obviously. So 0.71 is a unit weight is 24 of concrete. So 24 into 0.71 into 1 into 1. That is, you are calculating that over a 1 meter by 1 meter per square meter area. So this footing is 0.71. You have a column also here, and above that you have backfilling. So here you have backfilling. So a point here, this is 0.71, and this portion it is backfilling. So that backfilling is 18 kilonewton per square meter is the unit weight of soil, and 0.79 into 1 is the height. So that I have selected. So total you are going to get 169, 162.9, which is the gross bearing pressure. This shall be less than the SBC. That is one of the criteria. SBC is 180, so it is less than that. Then okay. So that dimensioning etc. is okay now. One way shear, two way shear, and the gross bearing pressure is okay. Now you can go for flexural reinforcement design. Here we assume that the dx dy whatever we have calculated, or the overall depth of foundation, is not going to be a criteria in flexure, because flexure criteria will be satisfied automatically with the design of shear criteria. Okay, so shear criteria is sufficient for flexure also, as far as the depth of foundation or thickness of that foundation is concerned. That is an assumption. As I told you, in classroom problems you assume this, but in real field problems, when you go to the field as an engineer, it is preferable that you check this depth also. You know how to check the depth whenever you know the bending moment of a slab. But here we assume, and generally this will be always true, this assumption will be always true. So for examination purpose, just find not calculate depth required for flexure, just to calculate the reinforcement required for flexure, that's all. So here we have two directions, one is xx direction and yy direction. So separately you need to calculate that reinforcement. So I have marked this xx direction here. So many items on the screen, but still you focus here now. You know the section xx is pass should pass through the column face. So that is what this line I have drawn, column face, and you know this is going to be 1700 based on our proportioning. So this is a cantilever. Okay, so this is the section. This cantilever is going to bend like this. So this is the span. Span is 1700 of the cantilever, and you know the loading. Loading is 1974 Newton per mm square is a uniformly distributed loading. So W L square by 2. So that is what we have applied here. WL square by 2, but we have a thickness of 3.8 meter. So that also I have taken, not the unit width 1 meter slab. Slab we do that for 1 meter slab, but foundation uh, you can do it for 1 meter slab and do the calculation. There is no issue. But in foundations, because it is acting as a total cantilever, the width 3800 has to come into the calculation. So that is a difference between slab design and footing design. Here the width has to come into your calculation fully. In slab, you need to bring into 1 meter strip. Okay, that is the basic difference between the structural action. Here the structural action is as a typical cantilever beam. That's why 3800 is included here. This is applicable in square footing design also. So 0.1974 we have already calculated is the breadth, and this is 1700 is the span, all square by 2. Okay. So mu x, that is long direction, 1084 into 10 raised to 6 Newton mm. Here also please mind, whenever you really are going to calculate this using your calculator, your notebook, your pen, this is going to be big figures. ഈ സ്ക്രീനിൽ കാണുന്ന കണ്ടിട്ട് എളുപ്പമാണെന്ന് വിചാരിക്കരുത്, വലിയ നമ്പറുകളാണ്, തെറ്റിപ്പോവും, എറർ പ്രോൺ ആണ്. Okay, now next you need mu by bd square. So I have calculated that mu is available here. B is the entire width of the cantilever beam, 3800, and dx is 625. We have calculated that earlier, 625. So 0.73 megapascal, 0.73 megapascal. Then from this stage, you can even use SP16 also to calculate the PT. Okay. And next is option is a formula. So this is FCK by 2 FY. You know that we have already derived it. So please make it by heart. 1 minus square root of 1 minus 4.598 is this a constant derived by us. 1.598 into mu by bd square by FCK, or use SP16 as you like. So what you are going to get is PT as this one. This is PT by 100. So 0.2115 is PT. Okay. And check whether it is okay as per the minimum requirement. So code says AST minimum, as we have done in the previous problem, it is 0.0012 BD. B is 3800, D is overall depth 710, 0.0012, that is AST is 3237. From that you can calculate PT minimum, that is 100 AS by BD, 100 into AST by B is 3800, D is the effective depth 625, you get it as 0.1363. So 0.1363 is the code requirement, minimum PT 0.1363, but our requirement is 0.2115 from the mu x value. We are satisfied, but the issue here is PT. Our assumption was for calculating tau C in one-way shear, one-way shear requirement, shear design. Our tau C was 0.36 was tau C. This was by assuming 0.25 as PT. Okay. But here from moment requirement, PT is only 0.2115. So we cannot accept this 0.2115 because it is okay as per moment requirement. But from shear one-way shear requirement, it should be 0.25. So this 0.2115 has to be rejected, and we have to accept 0.25 for further calculation of AST. Okay, so you adopt 0.25 for this particular case. That is, we are now in design for XX direction. So AST is 0.25 is the value accepted, and this is the B by D 3800 by 0.625, because this is XX direction. We are going to provide the reinforcement like this, of course, to be extended in this direction. So in this case, the breadth is 3.8, 3.8. Depth we have already calculated, dx 625 mm. Okay, so based on that, you get 5937.5 square mm as the AST. So we have assumed 20 mm dia bar, area of bar is 314. Pi into 20 square by 4 is 314. So you need 90 numbers to cater this AST. So you can check the spacing 202. Okay, how to get the spacing? Total 90 numbers in a width of 3800. That is, this is 90 numbers to be placed like this in a width of 3.8 meter minus cover minus half bar dia. So 20 by 2, 20 by 2. So it is 20 by 90 numbers means 18 spacings. So you get 202 mm as the spacing, and check that spacing as per clause 26.3.3 B of IS 456. You will get it is okay as per that. Some calculation you need to do this as per this. It will be around 300 or 3 times D, all these calculations. So you write that it is okay as per clause 26.3.3 B of IS 456, which is the maximum spacing permitted in slabs, or which the clause says about the maximum spacing permitted in slabs. Now, other direction. So you got the reinforcement like this, 19 numbers, 20 dia. Next direction, YY. So this is the section YY. There's so many items, but focus on this section, section YY. You know that that section is at 1700 from our proportioning. So section YY is clear. It's on the column face. Okay, that's why it is written here. Now look the calculations. Mu y 0.1974 is the this one in soil pressure, and now we have a cantilever beam like this. This is the cantilever beam. Fix a cantilever beam like this. This is going to bend up like this. Okay, so width of the beam is 4000, span is 1700, square by 2, so you get mux. Okay, I think these things are quite straightforward, nothing new in this. 1141 into 10 raised to 6 Newton millimeter. Then calculate mu by bd square and use sp16 or this formula. Using that formula, you are going to get a pt as 0.2256. This is also greater than our pt minimum as per code. AST minimum and PT minimum. PT minimum is only 0.1408. That is greater than the moment requirement or PT requirement based on moment. That's okay, but still issue in this case is not only that, our assumption was, as in the previous case, our assumption was 0.25 for one-way shear. So this is only 0.2256. So we need to discard this and use this. Okay. So adopt PT 0.25 for YY also, and AST is 0.25 is the area. Sorry, percentage. Area is okay. Now we are going to design reinforcement for this direction. So breadth is 4 meter. 605 is the effective depth. So from that AST is 6050, and if you use 20 dia bar again, you need 20 numbers. So you need 20 numbers. And check the spacing here. As I told you, this is going to be the direction of bar, so spacing available will be, or it is to be placed in 4000 width, 2 covers 75 into 2, and half 2 half bar dia. So that is 4000 minus 75 into 2 minus 20 by 20 bar means 19 spacing minus 1 spacing 202, so same thing. So I have told you what are the advantages. There are many advantages in selecting this projection and this projection same B and B. We have selected 1700 and 1700. If you don't have any space constraint in the site condition, so your calculation will be very easy, straightforward, and your checking also will be very easy. We have seen that in one-way shear calculation, only one equation was required. But if you select different values, you need two calculation in one-way shear itself, so that time can be saved. And also, when you use the same, projection, the spacing here you got 202, okay, in YY. In XX also you got that same 202. Here also you got 202. In XX also around same, not exactly, but so that is one of the another advantage when you use same projection. So generally, when we use almost similar spacing, if the projection in plan from column face is same, okay. So judiciously, if you are given with a problem without any space constraint, adopt this method in the design. As an alternative, if you are given with a space constraint, so that you cannot use 3.8 meter, you can use only say 3 meter, then same procedure, only difference is the plan dimensions. Procedure is one at the same. Even you can try to repeat the same problem by using this 3.8 as 3 meter, and the other dimension as 4.1 meter. You repeat the same problem, by using this as 3 meter used to due to space constraint, and this one has this one has 5 meter, 3 and 5 meter. Okay, try to do the same thing. Steps are one at the same. Just replace the numbers 3.8 with 3, 4 meter with 5. That's all. You can try that as a practice. So we have finished the flexure reinforcement calculation. So the design is now over. Some checking is especially for development of length. Sorry, development length, not development of length. Development length. Development length is required for, as I told you in the previous class also, or previous example also, for development of the bond. So development length is required for development of stress or development of bond. That is, reinforcement has to be securely held in position inside the concrete. So development length is required for development of bond. So LD. We have already calculated. Equation is given in the various clause and all. We have discussed that. Please listen the previous video from where you got 47 times diameter whenever the diameter in M20 and Fe415 is used. And in field, I told you it is around 50 dia. But in design calculations, don't use that. In field, you can use 50 dia development length or lap length also whenever you need to. Suppose you have a big slab or a big beam, say 20 meter as the dimension. But in market, the reinforcement available is only of 8 meter or 12 meter. You won't get 20 meter long reinforcement in the market because that is to be transported by a truck or trailer. So whenever you try to fix the reinforcement for 20 meter, you need to lap it. So the lap length between two bars, suppose you get a 12 meter uh, reinforcement, then one length can be 12 meter. Then to make it into 20 meter, you have a shortage of 8 meters. So don't 12 plus 8. Don't use 12 plus 8, but you need a 12 plus 8 point something. That is especially around 8 point something means 8 point say 8 plus LD. That is lap length also shall be LD. So 8 meter, don't cut it, 12 meter bar plus 8 plus LD. So if it is a 20 bar, LD will be 50 times diameter by thumb rule, so it is 1 meter. So in that case, 12 meter bar, then 8 meter, and the lap length is 50D is 1 meter. So 1 meter, 8 meter, 12 meter. This is what you should do in the field whenever you try to use the. So this is the lapping. Okay. Lapping is very simple one. No welding etc. is required. You can use the binding by using binding wire. Binding wire. Okay. So this is also equal to LD. So LD we have two uses for LD. One is when you need to lap a reinforcement. Another is when you need to check whether the development length for proper securation and development of stress etc. is to be ensured. Okay, that's all. Then now continuing discussion on LD 47 times 20 dia 940 mm. Available is in both directions. Here you have 1700. Here also you have 1700 because these are the critical sections for bending moment. So from bending moment critical section you have 1700 and you have 1700 this direction also. So that is greater than 940. Of course, minus cover 1700 minus cover 1625 is available. This is higher than 940. So LD condition is satisfied in this case. Okay. Now you can draw the reinforcement detailing plan 20 mm dia bar. Okay. In 4 meter dimension, you need 20 numbers. In 3.8, you need 90 numbers. Okay, and you can draw the section also. When you draw the section, try to draw something like this, some extra like this. This is also for the requirement of bonding and all. So like that, you complete the diagram. Okay, give the labeling like this, like this, and also try to adopt this in your AutoCAD drawing in future whenever you are trying to whenever you try to give a design, and when you try to detail it in an AutoCAD, try to use the same way. And of course, what you have to do is, as the final closing note, our design is over. The final closing note, you write the transfer, of course, which is given in clause 34.4 of IS 456. So please study that well, okay, and do that. Write that, which I have illustrated in the previous square footing case. Okay, so with that, we finish the two types of possible footing designs. Thank you very much.